In this video, we're going to cover nomenclature, so looking at different kinds of formula and the IUPAC rules for naming molecules, and isomerism, looking at different types of structural and stereoisomerism. Organic chemistry is all about the chemistry of different molecules containing carbon. Those molecules have different functional groups attached to them, so we're going to start off by looking at what we mean by a functional group. A functional group is the part of a molecule responsible for its characteristic chemical reactions. So basically, a functional group is what determines how a specific chemical will react. You'll have come across different kinds of functional groups when you've studied GCSE chemistry. You'll have looked at alkanes, alkenes, alcohols, and maybe a few other functional groups as well. A homologous series is a family of compounds that have the same functional group and general formula, and we'll look at what a general formula is in a moment, and they'll all have similar properties. So you'd expect any kind of molecule which is an alcohol to have similar properties and reactions. You'd expect any molecule which is an alkene to have similar properties and reactions. So we can call a group of molecules with the same functional group a homologous series. We'll now look at examples of a few different functional groups. We're going to look at ethanol, ethene, and ethanal. This is the functional group in ethanol, the OH group, and it is an alcohol functional group. So ethanol is an alcohol. This is the functional group in ethene, and this is an alkene functional group. So ethene is an alkene. And this is the functional group in ethanal. This is the aldehyde functional group, so ethanal is an aldehyde. We're now going to look at different ways of representing molecules. We'll look at some examples of these different representations. Now, some of these might not make complete sense until you've watched the full first section of the video, as in order to either name or draw molecules, you've got to understand the different ways in which you can name or draw them, but we haven't yet learned how to name them. So I'd recommend watching the full first section of the video, then you can recap this first section later on once you've seen where it leads on to. The first way you can represent molecules is by using the molecular formula. The molecular formula just gives the actual number of atoms of each element in a molecule. So for example, this is the molecular formula of ethanol. It tells you how many atoms of each element are present. So we know there are 2 atoms of carbon, 6 atoms of hydrogen, and 1 atom of oxygen. If there's only 1 atom of an element, we don't put the number 1, we can just draw it without the number. We can also use the structural formula to represent molecules. This is the most common way to represent molecules, as it gives you a bit more information than the molecular formula does. The structural formula shows the atoms carbon by carbon with all the attached functional groups and hydrogens. So for example, this would be the structural formula for ethanol again. We can see it gives us a lot more information than the molecular formula. We can see we start off with CH3, which is bonded to a CH2 and an OH. So the structural formula is a very quick way to get an idea about what the structure of that molecule is. You can also represent molecules using the displayed formula. The displayed formula shows how all the atoms are arranged and all the bonds between those different atoms. So this is a displayed formula of ethanol. We can see it's very similar to the structural formula, still a CH3, CH2 and an OH, but we can clearly see where all the bonds are. This gives a bit more information than the structural formula, but it takes a while to draw out, so in chemical equations we'll typically use the structural formula rather than the displayed formula. But exam questions could get you to draw out molecules using the displayed formula, and as you're getting to grips with chemistry, it can be a good idea to draw some molecules out fully displayed so you can get a good idea about what their structure is until you can recognise them in the structural formula. You can also use the empirical formula to represent a molecule. This gives you the simplest whole number ratio of the atoms of each element in a molecule. We don't typically use this as a way to write molecules in an equation, for an example, but as you go through the course, there are several times where the empirical formula is used, as it can be a way of experimentally deriving the formula of a particular molecule. We've looked at examples of ethanol so far, but the empirical formula for ethanol is also the same as its molecular formula, so we're going to look at a different example. If we had the molecule C4H8, the simplest ratio of the atoms of each of those elements would be CH2. So the simplest ratio of 4 to 8 is 1 to 2. We don't write the 1 in the chemical formula, so it is just CH2. There's obviously not an actual molecule with just CH2 because we know carbon has to have 4 bonds, so if they're just 2 hydrogens that would leave 2 bonds with nothing attached to them. But it's just a way of showing the simplest ratio of the elements within that molecule. When we were looking at the definition of functional groups and homologous series, we said they all had the same general formula, so we're looking at more detail what that means. The general formula is an algebraic formula that can describe any member of a homologous series. You'll probably use this quite a lot in GCSE when you learnt what the general formula for an alkane or an alkene was. This can be applied to any kind of molecule with a functional group. We don't typically use this widespread because there's other ways you can work out what the formulas should be, and you can draw the molecules out instead, so you don't have to learn the general formula for every kind of functional group like you imagine at GCSE. But you need to be able to write or figure out the general formula for a given molecule. So the general formula for an alcohol is CnH2n plus 1 OH. So that means for every carbon, there are twice as many plus 1 hydrogens and an OH group. Finally, you can also use skeletal formula to represent a molecule. This is quite a common way to represent molecules in chemistry, and we'll look at some further examples of how to draw these after we've gone through this page. So the skeletal formula shows the bonds of the carbon skeleton only. We don't show any hydrogens, but we would show other functional groups. So for example, this is the skeletal formula of ethanol. We're going to look at further examples of these in a moment, but simply each point on the skeleton, so for example here and here, represent a carbon with the other functional group, in this case OH added on. This would be the skeletal formula for pentane. That's because there are 5 carbons in the skeletal formula. We've got 1, 2, 3, 4, 5 essentially nodes or points on the line, and this is how we'd always draw a skeletal formula in this kind of zigzag way, where each of these points here represents a carbon. So if we were to write this molecule out structurally or using the structural formula, it would be CH3, CH2, 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 CH3. Because we don't draw on any hydrogens, we assume that the hydrogens are on there. So for example, if we look at this carbon here, there are 2 bonds coming off it. Therefore, it must have 2 other bonds to hydrogens. So we know this carbon here must be CH2. We know this carbon here must be CH3, because we know that carbon has got 4 bonds. We can see 1 bond coming off it, so the other bonds must be to hydrogens, therefore this must be a CH3. We can show double bonds in skeletal formulas as well. So in this case, we've got propene, we've got 3 carbons because we've got 3 points in the diagram, 1, 2, 3. And we can see here we've got a double bond between these carbons. Again, we assume that any bonds not shown in the diagram are to hydrogens. So this is our CH3 because there's 1 bond coming off it, so it must have 3 hydrogens. This will be a CH because we can see 3 bonds coming off it, so there must be 1 bond to a hydrogen. And this will be a CH2 because there are 2 bonds coming off it, therefore there must be 2 bonds to hydrogen, to make it each carbon have 4 bonds in total. We can show other functional groups, so for example, where there is an atom which isn't carbon or hydrogen, we would draw those on. So in this case, we've got 4 carbons, as we can see from the 4 points of the diagram, and on this carbon here, there is a double bond to an oxygen. So we could write the structural form of this molecule as CH3, CH2, C with a double bond to oxygen, which in this case I've drawn like this to make it really clear, and then a CH3 group at the end. Again, making sure that each carbon has got 4 bonds, where any bonds not drawn in the diagram are assumed to be to hydrogen. You can also have slightly more complicated diagrams. I've drawn this one just to illustrate where you would put the different bonds on. So once you've gone beyond your zigzag, where there is essentially like an arrow point, those bonds go directly up or directly down, and then they come off at an angle on the other side of the arrow point. We're now going to start looking at how to name molecules. We're just going to start by looking at how to name alkanes with the straight chains, and then we'll look at ones with branch chains coming off. Once we've looked at how to name the main chains or the carbon skeletons of a molecule, we'll then look in more detail at each of the different functional groups. We're going to start by looking at how long the chain is and what stem that gives to the name. You need to be able to name chain lengths of up to 6 carbons in length. If a molecule has 1 carbon in the chain, the stem of the name would be meth. So for example, from GCSE, you'll be aware there is methane. If we've got 1 carbon, we use the stem meth. 2 carbons give the stem eth. 3, prop. 4, bute. 5, pent. And 6, hex. So for example, if we were going to start naming this molecule, we'd look at how many carbons are in the chain. There's obviously just 1 carbon here. So this would be methane. So if we had to write the name of the molecule, or if we were just given the name and we wanted to know how many carbons were inside, we'd look for the stem, meth, and we'd know it has 1 carbon. We're going to look at the functional groups separately in a moment, but if we just wanted to work out what stem this molecule would have, again, we'd identify the number of carbons. And there are 4 carbons in this chain, which means the stem of the name would be bute. We'll look at the functional group, the alcohol group, later on. To start off with, we're just identifying what the stem would be. We can also do this skeletally, as we've just looked at a moment ago. There are 5 carbons in this case, so the stem of the name would be pent. And you might recognise this molecule from GCSE if you looked at this previously. This would just be pentane. This molecule has 3 carbons in its chain, so the stem of the name would be prop. So this is propanal. Not all molecules are just straight chain, like we've looked in the final example of how to draw skeletal ones. So we're now going to look at how you can name molecules where they've got their main straight chain and other alkyl groups coming off it. Again, we'll look at how long these side chains are and what name we will give them. You only need to be able to name side chains up to 3 carbons in length. We'll look at examples of what these look like in a second, but if your side chain has got 1 carbon in it, we would call that a methyl group. If your side chain has got 2 carbons in it, we'd call that an ethyl group. And if your side chain has got 3 carbons in it, we'd call that a propyl group. We also need to know how to name multiple of these groups on the same molecule. If we have 2 of the groups in the same molecule, we'll use the name di, 3 groups tri, and 4 tetra. So let's put this all into context with an example then. So I've drawn out a molecule here, which has got a straight chain and a side chain, so something coming off the main chain. It's important that you can identify what the longest chain in a molecule is, and you've got to do this in one continuous chain. So for example, the longest chain is 4, because if we start here and end here there's 4 carbons. We could start on the side chain, but the longest chain would still be 4. We could have a chain of 3 carbons if we went this way, or a chain of 4, 1, 2, 3, 4, if we went this way. Whichever way we look at it, there is a longest chain of 4, with then a side chain of length 1. To make it easy and to illustrate the naming, we'll highlight the longest straight chain in yellow and the side chain in green. We'll cover the full rules for how to name a molecule and combine the different parts of the name together after we've looked at the functional groups, but we'll start to look at a few examples of that now. This side group, highlighted in green, is going to be called 2-methyl. It's going to be called methyl because it's the side chain, it's not on the main chain, and there is 1 carbon in this side chain. We know if the carbon in the side chain has got a length of 1, we've got the name methyl. We've written the number 2 first, so we know which carbon on the chain it's on. We always try to get the number to be as small as we can, and we'll do some more practice on this later, but we essentially have got a choice of numbers. If we number the carbons in the yellow chain from 1 to 4, if we started here, the numbers would be 1, 2, 3, 4, in which case our methyl group would be on carbon 3, but we could also number the chain 1, 2, 3, 4, going from right to left. It doesn't matter which way round you number the chain, you can do it either way round, but we want to number it whichever way round will give us the smallest numbers. We had the option of it being 3 if we went from left to right, or on carbon 2 if we went from right to left. 2 is obviously smaller than 3, so we'd number our carbons 1, 2, 3 and 4, therefore the methyl group is on carbon 2. The remaining chain has got 4 carbons in, so we'd call this molecule 2-methyl-butane, because there is a methyl group on carbon 2 of the butane molecule. This example is drawn skeletally, but would go through exactly the same process. We have got 6 carbons in the main chain, and we have got 2 carbons in the side chain. So we'll look at how we'll name that side chain first. It would be called 3-ethyl. 3 because it's on carbon 3. Again, we could have the option of it being on carbon 3 or 4 depending from which end we start on. We want the number to be as small as possible, so we'll pick 3 rather than 4. We call this group an ethyl group because there are 2 carbons in that group, and if we've got 2 carbons, we use the name ethyl. So this is an ethyl group. It's on a hexane molecule. It's got 6 carbons on it. So the name would be 3-ethylhexane. There's an ethyl group on carbon 3 of the hexane molecule. This time, we've got 2 side chains of the molecule. It's not going to affect how we name it. We're going to go through that same process again. The longest straight chain has got 5 carbons in it. We've got 1 side chain here with 1 carbon in it, and another side chain here which has got 2 carbons in it. The ethyl group is on carbon 3, ethyl because it's got 2 carbons in it. The methyl group is on carbon 2. And there are 5 carbons in the main chain, so the name would be 3-ethyl 2-methyl pentane. We'll look at all the rules for naming again in more detail later on, but the order we put the groups in is in alphabetical, not based on the numbers. So because E comes before M in the alphabet, we put the ethyl group first and then the methyl group. Doesn't matter what the numbers are. So the molecule's name would be 3-ethyl 2-methyl pentane. We'll tackle this molecule in exactly the same way. So we'd start off by identifying what the longest chain is, in this case 5 carbons. And then we've got 2 side groups, each with 1 carbon in. So for these groups, we would write 2,4-dimethyl. 2 and 4, because the methyl groups are on carbons 2 and 4. Dimethyl, because there are 2 methyl groups in the molecule. So 2,4-dimethyl means on carbons 2 and 4, we've got a methyl group. The dimethyl doesn't mean 2 methyl groups on each carbon, it's just a number of methyl groups in total. So if you see dimethyl, that means there are 2 methyl groups in the molecule. If we had 3 methyl groups in the molecule, we would write trimethyl. If, for example, we had 2 methyl groups on the same carbon, so for example, if we had another methyl group here, in which case then we would call it 2,2,4-trimethyl, and would do 2,2, would write the 2 twice, because both methyl groups would be on the same carbon. As it stands though, to finish off the name for the molecule we've drawn, it would just be 2,4-dimethyl pentane. We're now going to look at all the different functional groups. We're going to look at their name, how we would add their name to a molecule called the prefix or the suffix. So if there's a prefix, that part of the name will come at the start of the molecule. If there's a suffix, that part of the name will come at the end of the molecule. We'll draw out the functional group and we'll give an example of a molecule with that functional group. We're going to start off by looking at alkanes. We use the suffix ane to represent an alkane in a molecule. And the functional group is simply carbons single bonded together. This will be something which you will have looked at before in GCSE. So this could be an example of an alkane. Here you can see that there's only the single bonds, just like we drew in the functional group above. And we would call this ethane. So you can see the suffix ane at the end, representing that this is an alkane. Alkenes will have the suffix ene. Their functional group is 2 carbons double bonded together. And an example would be ethene. Again, you can see the suffix at the end of the name. There are 2 carbons, so the stem will be eth. Put in eth and the alkene together gives you ethene. An alcohol has both a prefix and a suffix. This is because an alcohol is quite a common functional group. Typically in molecules we only have 1 suffix in the name. Because if alcohols are very common, you could have, say, an alcohol group and a different group on a molecule at the same time, we need to have the option of a prefix or a suffix. Typically, you will just use the suffix -ol when naming an alcohol, but later, probably towards the end of year 13, you'll come across some molecules which have both an alcohol and a different functional group. If that other functional group, if it's named by using a suffix, you would use the prefix hydroxy instead to denote an alcohol. So the examples we're going to look at throughout this topic will use the suffix -ol. An alcohol functional group is an oxygen bonded to a hydrogen attached to a carbon. So for example, this would be ethanol. A halogenoalkane is any halogen bonded to a carbon. You could have either a bromine, chlorine, fluorine or iodine, depending on which halogen is present on the molecule will determine what prefix you use. So for example, if it was a bromine attached, you'd use the prefix bromo. If it was a chlorine attached, you'd use the prefix chloro. As a halogenoalkane could be any of the halogens attached, when we're using general representations, we typically use an X, and an X just means it could be any of the halogens, chlorine, bromine, iodine, or fluorine, and that atom is just attached to a carbon. So for example, this would be chloroethane. The suffix -al, and the functional group is a carbon double bonded to an oxygen with a hydrogen also attached. This means it has to come at the start or the end of a molecule because there's only one other direction the chain can go in, and that is from the carbon to the rest of the chain. Therefore, it has to be at the start or the end. So for example, this would be ethanal. A ketone has the suffix -one. It's very similar to an aldehyde. The only difference is it occurs in the middle of a molecule, so there's no hydrogen here. Instead, there'll be carbons either side of it. So for example, this would be propanone. Carboxylic acids have the suffix -oic acid. The functional group for a carboxylic acid is a carbon double bonded to an oxygen with an OH attached to the same carbon. So this is all one functional group. It's not, for example, an aldehyde or a ketone joined onto an alcohol. This entire thing is one functional group. Like with the aldehyde, because there's only one direction the rest of the chain can come off in, this will always be at the start or the end of a molecule. So for example, this would be ethanoic acid. Nitrile functional groups just have the suffix nitrile. The functional group for a nitrile is a carbon bonded to a nitrogen, and it has a triple bond between them. So for example, this would be ethane nitrile. They're named a little bit differently, where nitriles are just named using the name of the alkane and then putting nitrile at the end. So ethane nitrile. It's important to remember the carbon which is part of the functional group here does form part of the longest chain. So it's not methane nitrile. The whole functional group is the nitrogen part here. So the name is ethane because there are two carbons, and then nitrile. Like nitriles, amines are quite straightforward to name. They just have the suffix amine. An amine functional group is an NH2 attached to a carbon. So this molecule would be ethylamine. Unlike nitriles, we name amines by using the name as if it was a side chain. So the two carbons in the chain we would call ethyl and then put amine at the end. If there was one carbon in the chain, we would call it methylamine. We're now going to look at the rules for how to name molecules, and we're going to work through a series of examples to put those rules into practice. The first thing to look for is, does a functional group have to be at the end? We've looked through a few examples already, things like aldehydes and carboxylic acids, which have to go at the end of the molecule. You then need to determine what the longest chain is. If we have one of those functional groups which has to be at the end of the molecule, that will be part of the longest chain. So by identifying if there is a group which has to be at the end first, that will tell you where the chain has to start or end. If there isn't a functional group which has to go at the end, you'll have a bit more freedom with where the chain can start or end. You then need to identify and name where any additional groups are and where they are on the carbon skeleton. Make sure how you number the skeleton is arranged so you use the lowest set of numbers possible, like we looked at earlier. Then make sure all the functional groups are added to the name in alphabetical order. And finally, use a dash to separate a number from a letter in the name, and use a comma to separate two numbers in the name. We'll look through some examples of these now. So we'll check, does a functional group have to be at the end? In this case, there is no aldehyde or ketone, so we'll now go on to identifying the longest chain. There are 5 carbons in the longest chain, so the stem of the name must be pent. I'm not going to try and write the name with the correct parts in the correct order to start off with. I'm just going to identify all the different bits of naming and I'll put them together at the end. I have got 2 alcohol groups in this molecule, and they're on carbons 2 and 4. So this section of the molecule would be called 2,4-diol. 2 and 4 because the groups are on carbons 2 and 4. Di because there are 2 of these functional groups, and ol because that is the suffix for an alcohol functional group. We've also got a bromine atom on carbon 3. So this would be called 3-bromo. 3 because it's on carbon 3, and bromo because that's the prefix for a halogenylalkane functional group. We then put all of these parts of the name together to give us 3-bromo pentane 2,4-diol. In this case, we don't need to worry about the alphabetical order because we've got a prefix, the stem of the name, and a suffix. So that's the only order this can go. When we look whether things are in alphabetical order or not, that's when we have multiple prefixes, for example. But in this case, we've got a prefix of bromo, pent as the stem, and then a suffix as 2,4-diol. So altogether, the name for this molecule is 3-bromopentane 2,4-diol. We include the full name pentane here because we're naming it as a diol. Hypothetically, if this molecule just had one alcohol group, say on carbon 2, the name would be 3-bromopentan 2-ol, like we looked at when we were looking at how to name the functional groups. But because there is more than one alcohol group, we use pentane, diol in this case. For this molecule, we'll identify if a functional group has to be at the end first, and it does. We can see here we've got the carboxylic acid functional group, so that must be part of the main chain, and it also must be carbon 1. So if a functional group has to come at the end, this will be carbon 1 in the chain. Even if numbering it in a different way can make the number smaller, that doesn't matter. If one of those groups has to go at the end, it has to be carbon 1. And that's because we don't include the numbers for things which have to be at the end. We'll then identify the longest chain, including that functional group. In this case, that's 4 carbons, meaning the stem of the name will be bute. And again, I'm just going to identify all the different bits of the name and we'll assemble it together in the correct order at the end. We've then got our carboxylic acid functional group, which means we're going to use the suffix oic acid. Because it has to go at the end, therefore it has to be carbon 1, we don't need to include 1 oic acid or any kind of number in there. We know it's got to be carbon 1, so we don't need to add the number 1 into it. And we've also got an OH group on carbon 3, because again, this has to be carbon 1. So 1, 2, 3, the OH group will be on carbon 3. We have a choice for an alcohol. We can either use the prefix hydroxy or the suffix ol. We've already got a suffix in this molecule, and we tend not to use multiple suffixes. So given we've already got a suffix from oic acid, we're going to use the prefix hydroxy. It's on carbon 3, so we'll call this alcohol group 3-hydroxy. The name of this molecule is therefore 3-hydroxy butanoic acid. Like the example we looked at a moment ago, we've got a prefix, the stem, and the suffix. So there's only one order we can put these in, prefix, stem, then suffix. So it's called 3-hydroxybutanoic acid. This molecule looks a bit more complicated, but we can go through exactly the same process again. We're going to start off by identifying if it has a functional group which has to be at the end, and it does. The aldehyde group has to be at the end. It's one of the two groups, along with the carboxylic acid, which have to be at the end. Therefore, this has to be part of the longest chain, and it will be carbon 1. So therefore, the longest chain has got 5 carbon atoms in. This is why we have to identify that the aldehyde has to go at the end at this stage here, because we could actually have a longer chain of 6 carbons if we started up here with 1, 2, 3, 4, 5, 6. But if we numbered that way, the aldehyde group wouldn't be part of the chain, it couldn't be carbon 1, so that wouldn't match the rules of naming. That's why we have to identify which functional group has to be at the end, or if there is a functional group which has to be at the end first. So we've got a longest chain of 5 carbon atoms. This means the stem of the name is going to be pent. We've got an aldehyde group here, and we know that's on carbon 1 in the chain, and like with the carboxylic acid, if it's got to be at the end of the molecule, we're not going to add the number in because we already know it has to be at the end. So we use the suffix -al. We have then got 3 methyl groups. We've got a methyl group on carbon 2, and a methyl group on carbon 4, and another methyl group on carbon 4. So this part of the name would be 2,4,4-trimethyl. 2,4,4 because the methyl groups are on carbons 2, 1 and 4, and a second and 4. Trimethyl because there are 3 methyl groups in total. We then have an ethyl group, which is on carbon 2. So that part will be called 2-ethyl. So putting that all together gives us a name of 2-ethyl, 2,4,4-trimethyl, pentanal. Remember, we have to order it in the name of prefix first, then stem, then suffix. We've got a choice of 2 prefixes, so we need to put them in alphabetical order. When we're determining the alphabetical order, we don't take into account any letters telling us how many of those functional groups there are. So we don't take into account di, tri, or tetra, we pretend they're not there, so we would use the M of methyl against the E of ethyl. E comes before M in the alphabet, so the order is ethyl first, then the methyl group, in this case it's a trimethyl group, but remember the di, tri, and tetra don't affect the alphabetical naming. So our overall name is 2-ethyl, 2,4,4-trimethyl, pentanal. We're now going to look at different types of isomerism. Again, like we did with the functional groups, we'll go through them all in one go first, and then we'll look at specific examples of each afterwards. The first type of isomerism we're going to look at is called structural isomerism. This is where molecules have the same molecular formula but different structural formulas. You might want to go back to the first section of the video and recap what these different types of formulas mean. So we could say that 2 molecules are structural isomers of each other if they have the same molecular formula but their structural formulas were different. So let's look then at some examples of this. Let's look at the structural isomers of C4H10. So C4H10 could be this molecule here with 4 carbons in a straight chain, which is obviously butane. But C4H10 could also make this molecule here with 3 carbons in a straight chain and 1 carbon, a methyl group, coming off. This molecule would be called 2-methylpropane. So we could say that butane and 2-methylpropane are structural isomers of each other. They both have the molecular formula C4H10. They each have 4 carbons and 10 hydrogens in total, but they've got different structural formulas. Another type of isomerism is chain isomerism. This is where molecules have the same functional groups but a different arrangement of the carbon skeleton. We're just going to look at these in terms of different kinds of alkanes. So we're going to look at the different chain isomers of C6H14. This is one way of drawing C6H14. We could also draw it as a chain of 5 with one methyl group. We could draw it as a chain of 4 with 2 methyl groups coming off. And again, we could draw it as a different chain of 4, but we could have both methyl groups coming off the same carbon. So this is chain isomerism because the carbon skeleton has changed in each of these different examples. Chain isomerism is a type of structural isomerism. So these molecules will have the same molecular formula, but a different structural formula. But this is a specific type of structural isomerism called chain isomerism. We're going to have a look at another kind of structural isomerism now. So positional isomerism is a different kind of structural isomerism. It is where the functional group is attached to a different part of the same carbon skeleton. So we're not going to change the carbon skeleton this time. If it was a straight chain of 6, it will still be a straight chain of 6. We're just going to move the functional group around within that carbon skeleton. So for example, this is 1 chloropentane. The chlorine is on carbon 1 of the pentane chain. But we could also have 2 chloropentane here, or 3 chloropentane here. So we would say that these are positional isomers of each other. They've got the functional group attached to a different part of the skeleton. They're also structural isomers of each other, but positional isomerism is a subset of structural isomerism. The final subset of structural isomerism is functional group isomerism. This is where molecules have the same molecular formula, but they have a different functional group. There are 2 specific examples of functional group isomerism that you need to know. We're going to start off by looking at C3H6O. This could be an aldehyde, in this case propanal, but it could also be a ketone, propanone. So these 2 molecules are functional group isomers of each other. They've got the same molecular formula, but a different functional group. Like I said a moment ago, you do need to know specific examples of these, so you need to know that aldehydes and ketones can be functional group isomers of each other. The other example we're going to look at, we'll use C4H8 as the molecule. So this could be an alkene. In this case, I've drawn but2-ene. But it could also be an alkane. Now, it'd have to be a special kind of alkane, and we call these cycloalkanes because you can see it's in a ring. You can imagine 4 carbons joined together in a square, and both of these will have the molecular formula C4H8. If you think back to the work you did at GCSE, you might think that this molecule has to be an alkene because it's got the molecular formula C4H8, which matches the alkene general formula of CnH2n, but that's not a hard and fast rule. This is a cycloalkane, where it's in a ring, so as long as you've got a ring in that molecule, it'll be a functional group isomer of an alkene. So we can say that alkenes and cycloalkanes are functional group isomers of each other. The second main kind of isomerism is called stereoisomerism. Stereoisomerism is where molecules have the same structural formula, but how those atoms are arranged in space are different. We'll look at some examples of this. The first type of this is called geometric or EZ isomerism, and this is something which you cover in Year 12. The second type is called optical isomerism. You'll have a separate topic looking at this when you start your Year 13 work, so we're not going to cover this in this video. It forms under the separate topic 3.3.7. So geometric, also referred to as EZ isomerism, and we'll look why in a moment, is where molecules have the same structural formula but different arrangements of the atoms in space caused by a restricted rotation of the carbon-carbon bond. We're going to use an example to explain what this means. So if we look at this alkene here, and we need to have an alkene because our definition says we've got to have a CC double bond, we can see we've got two different groups on each side of the double bond. We've got a CH3 and a H, and on this side we've also got a CH3 and a H. Now, double bonds have restricted rotations. It means this molecule can't rotate around the double bond. It means the orientation of this molecule is fixed. In this case, it means that both of these CH3 groups will be pointing upwards, they'll be pointing in the same direction. I could also draw this molecule like this, with one of the groups pointing up and one of the groups pointing down. Because double bonds can't rotate, this group can't rotate around the double bond to end up at the top. These two molecules are different. They've got exactly the same structural formula, the atoms are attached in the same order, but they're arranged differently in space. One of these molecules has got both of the biggest groups pointing up, the other one has got one of the biggest groups pointing up, and the other group pointing down. So this is why they are geometric isomers of each other. If both of the biggest groups are pointing in the same direction, either both up or both down, we say that's the Z or the cis isomer. If both of the groups are pointing in opposite directions, so one of them pointing up and one of them pointing down, we call that the E isomer or the trans isomer. This is why the name can sometimes be called EZ isomerism. We're going to look at a few examples and determine whether they are E isomers or Z isomers. So in order to determine which isomers we've got, we need to look what sides the biggest groups are on. We can see in the left molecule, both of the biggest groups, the chlorine, are facing the same direction. In this case, they're both facing up. On the molecule on the right-hand side, one of the chlorines is facing up, while the other is facing down. Therefore, we've got the Z isomer on the left, because the groups are pointing in the same direction. And the molecule on the right is the E isomer, because the two groups are pointing in opposite directions, one up and one down. Therefore, the molecule on the left would be called Z, 1,2-dichloroethene. The molecule on the right would be called E, 1,2-dichloroethene. If we wanted to identify what isomer this was, again, we'd see which directions the biggest groups are pointing. However, in this case, we can see we've got two identical groups on the left-hand side. This would cause us a problem, as we can't tell whether the groups are pointing up or down because they're the same. In order to have EZ isomerism, you've got to have two different groups on each side. Doesn't matter what the groups are on each side. If this bottom CH3 group was a fluorine, an F for example, that would work. They don't have to be the same two groups on each side, but you do need to have two different ones. If you've got two identical groups, they can't be pointing in different directions, therefore the molecule will not show EZ isomerism because there are two of the same group on at least one of the sides. And sometimes you might have to justify why a molecule doesn't show EZ isomerism. we use something called the CIP priority rules to help us determine whether we've got an E or a Z isomer on slightly more complicated alkenes. The first rule is that you assign priority to atoms where the atom with the highest atomic mass has the highest priority. If you have two of the same atoms on a side, you then look at the next atom along and assign priority to whichever atom's got the highest mass. If they're the same, you keep going until you found a difference where you can assign priority. We'll look at an example now where this will make a little bit more sense. So if we look at this molecule here, we'd have to decide which atoms were the highest priority on each side. The atom has got the highest priority if it's got the highest mass. So bromine has got a bigger mass than fluorine. You might need to use your periodic table to check this out, but bromine would have the highest priority on the left-hand side, and it would also have the highest priority on the right-hand side because it also has a higher mass than chlorine. Now we've highlighted the biggest group, the highest priority groups on each side. We can see that they're pointing in different directions. Therefore, it must be the E isomer. Again, we'll do the same for this molecule. Bromine still has a higher mass than fluorine, so bromine's the biggest group on the left-hand side. It has the highest priority. We've got a chlorine and a carbon on the right-hand side. Chlorine has got the highest atomic mass, therefore it's got a higher priority than carbon. This means our two groups with the highest priority are on the same side, therefore being the Z isomer. For this molecule here, once again, bromine has got the highest priority on the left-hand side because it's got a higher mass than the chlorine, but we've got two carbons on the right-hand side. These are different groups. This is a methyl group effectively, and this is an ethyl group, so it will show EZ isomerism, but we've got to decide which has got the highest priority. As both of the first atoms we've looked at are the same, both carbons, we'll then move to the next atoms along. In this case, 3 hydrogens. In this case, 2 hydrogens and a carbon. Hydrogen has a mass of 1. Carbon has got an atomic mass of 12. 12 is bigger than 1, therefore this side down here will have the highest priority because after the first atom, we've got a choice of one of 3 hydrogens or one of 2 hydrogens and a carbon. Carbon having the highest mass will have the highest priority. Therefore, the highest priority group is on the bottom in this case, and the top in this case. They're on different sides. So this molecule will be the E isomer. Finally, for this molecule here, bromine, again, has got the highest priority on the left, and we've got 2 identical groups on the right. If we've got 2 identical groups on the right, both being CH3s, we can't assign priority. Therefore, this molecule will not show EZ isomerism.